Good morning, and thanks for having me. My name is Greg Roberto, and I work at the Barcelona Beta Brain Research Center as head of neuroinformatics. And for you to know, for several years I used to work both as a researcher and as the guy behind the image processing platform. And this dual position is important to stress, as I think it had a large influence on what I'm going to talk about now. About the scope of today's talk, you'll hear me talking about a particular model that we have developed here in Barcelona, because this is what I know best, what we worked on the most, and actually most of what I will talk about is going to be drawn from that paper that we published 1 year ago. Now, as processing and controlling data is obviously a huge subject, instead of picking some tools, presenting them, saying, okay, folks, this is how you do things and that's it, which would be impossible and simply lying, today, I prefer to give more emphasis on the story around our model. So hopefully you may relate to some parts of it, and then the reasoning, the principles, the best practices, the choices made will sound much more natural to you. I will aim to raise questions that you should ask yourself as data managers while looking for the best system for efficiently managing, processing, controlling large data sets, given your environment, skills, preferences, resources, etc. So just some approach that worked for us, and we made it such a way that you can adapt it to other centers. Like, imagine you're a young investigator in a young or small research institution with their own cohort studies or simply acquiring their own imaging data. So you have to deal with large neuroimaging data sets. You have to come up with some way to collect, process, review, control that data. Still, you're facing certain constraints like limited resources plus strong publication incentives. So you need to find the right balance between investing your time into a robust system to manage your data and getting your research done. And so again, that's been more or less my story for the past 5 years, in a particular context, the Barcelona Beta Brain Research Center. The center was created in 2012 as a center dedicated to prevention of Alzheimer's disease, and in this context was initiated the Alpha project as a research platform for the follow-up of a cohort of cognitively normal subjects, most of which are the offspring of AD patients. That building in the center of Barcelona is the BBRC, where the Alpha participants come for extensive phenotyping with cognitive assessment, lifestyle questionnaires, blood extraction for blood-based markers and genetic analysis, and multimodal MR imaging performed on-site on this Philips 3D scanner. Then a subset of these subjects has a lumbar puncture for CSF collection and also PET imaging with amyloid, FDG, and tau tracers. All in all, counting Alpha plus external projects that come to BBRC, that's over 5,000 subjects that went in the scanner, and there you have a rough idea of the needs in terms of data collection, image processing, quality and provenance control, etc. In our case, data follows this kind of typical itinerary, starting with the participant inclusion. They get assigned with some ID. Then the imaging part takes one way, the non-imaging part takes a different way, which is not described here. MR scans are acquired at BBRC, while PET imaging is done at another center in Barcelona, and then every scan is imported into an XNAT platform through a CDP service for anonymization. And the raw data is also backed up on a PAX and a Philips portal. The platform is open to some external collaborators who may also push data in different projects, but then that's a management that is independent from the Alpha study. And then once the data have been successfully imported into XNAT, imaging sessions are then taken through processing workflows. This is managed automatically by the XNAT pipeline engine, or now the recent container service, which sends those workflows to the computational nodes, or, it can be a cluster, or it can be a single Xeon machine. We mostly go by the latter option, for instance. And those workflows include processing, meaning all types of neuroimaging software, or published methods, algorithms, but also automatic controls based on validators, which I will talk about in a couple of slides. And this results in the generation of derived images, numeric endpoints, and validation reports. And along with the raw data, all of this forms the body of online resources that users can reach simply by logging into the system. I mentioned XNAT, which, as you can see, holds a central place in the data flow. Now, what is it? Basically, it is a piece of software, a software suite for managing neuroimaging data. And what other big options did we have at this point to facilitate data management or processing? I would say that today there are three main strategies available to research groups that I call the BIDS way, the XNAT way, and the Science in the Cloud way, each of which being characterized by, first, the general amount of IT skills required to operate the system, and by this I mean in a typical multidisciplinary like an Alzheimer's research group, all right? Then, some dependency on the cloud, like you cannot always push everything online from day one, especially if this is not your data. And then with some costs. There are more and more commercial platforms that offer science as a service against money. You send your data, they get everything done for you, and you're happy. Okay, so now I can't get into much more detail in this comparison for the sake of time. Chances are that other speakers may elaborate more on the BIDS framework, or you can anyway find a lot of great online resources on the subject. So if you're looking for an open source system with built-in features to receive the icons from some equipment, some graphical and user-friendly interface to manage raw sessions, processing workflows, access permissions to a local repository, some software that has continued support and an active community, well, there are actually quite few options out there, and no doubt why XNAT is probably the most deployed one. And one important point, and I put it at the end, is that XNAT comes with an API, and I will come back to this. So for those not familiar with it, here's a screenshot of XNAT web interface where you can see the various hosted studies or projects, text boxes for queries, and a list of recent activity on the platform. Now, let's imagine a real case scenario. You need to run a voxel-based analysis, and for that you need to collect a whole collection of gray matter segmentations. So normally you would have first to generate those segmentations by yourself, but let's imagine you are at BBRC, so you can rely on a platform that has processed this data for you. And then you can use XNAT's web interface to download those segmentations, and you will quickly realize that it will take tons of clicks to get them on your disk. And after that, you will still need to reorganize the files, maybe rename them, put them in the same folder, etc., etc. While in the end, what a researcher wants usually is a single structured folder with many files of the same resources, here RC1 and RC2 if we're using SPM, for instance, named by their subject ID, something to be fed directly into some group analysis software. And as I said, with XNAT, there are two main ways to interact with the data. Either you get your preferred mouse and start clicking on the web interface, or you can use the REST API. And then if you can code, you could write a script to get to download the same data directly in your desired format. And luckily for us, this REST API can be operated in Python. So here I show how you can interact with subjects, experiments, resources, processing results. This is for hippocampal subfield volumetry. This one takes one session, gets the APARC results from FreeSurfer as a data frame, and then we just plot the thickness values on a cortical model. This is for white matter lesions. These are just examples. This, of course, depends on the type of data that you have in your study, but the key thing here is about how you interact with data from the source. This way we could somewhat be close to being able to run a full analysis directly in a single Jupyter notebook, you see. So time for one practical example. After registering on Central XNAT, that's a good moment to try and log in the platform and discover the various features around. There will be a project called tutorial, which is quite basic, quite empty. I just made it with some minimal resources so to allow you to take some first steps with the API. And this notebook will be available for you to be able to follow these instructions. So once again, two main ways to interact with XNAT, one rather for the coder, one for the wider audience. Then we realized that between all clicks and all code, there's a large gray zone with users who, without being Python gurus, can still use some command line tools. And for this category, we wrote a tool called BX, which allows us to run from a terminal among a set of bulk operations, as we will see now. Like you remember this one with the SPM segmentations, well, this is achieved with a single command here, bx spm12 rc, name of the project, destination, and there you go. In your folder, you get all the RC maps. And this is for voxel-based outputs. Now, what about numeric endpoints, like free surfer cortical thickness? There's even a mean for this. So bx free surfer 6 or 7 aparc for a whole project, and there you go. All the stats from free surfer aparc for all the subjects in one spreadsheet. Here's a list of the commands that were available when I prepared this slide. All commands share the same template, which means running them is done typing bx command name, then some subcommand if necessary, then some data identifier. What is the take-home message here? Of course, bx will not work for you unless you have the same data in your project as us. But the beauty here is how you can, at any time, collect some fresh data from the source over the whole cohort in some perfectly consistent and systematic way, and avoid having to rely on the same old Excel tables that were generated some months, years ago. We don't remember how or by who. So that's quite an asset for reproducible research. I prepared some quick example for you to get some feeling of it, and for this example you need your previously created account on Central XNAT. You will need to pip install the package called pbrc-bx and the configuration file that you should have created in the previous example. And then you should be able to run the following commands, and then just look for these files, and this is where you should find the collected data. Okay, one more example with hippocampal subfield segmentation. In this case, bx hashes volumes with the name of a project, for instance, and you would then get this spreadsheet. So hashes for hippocampal subfield volumetry, and this data could be already usable in your analysis workflow. Now, some typical question here would be, how do I know that I can use this data, that segmentation was correct? And that makes my transition to the next part more about QC. So this is how you would collect, for instance, a series of automatic tests performed on the data right after the segmentation without anybody looking at it yet. This command is bx hashes tests and data identifier. Here, that's a big one with 1,500 subjects. So that would generate a big Excel table with 1,500 rows, and in columns, the various checks. And we can then refer to red cases. For instance, I want to check this one with 3 failed checks. So I would pick the session ID and then use it in a command, bx hashes snapshot. And there I can see that the segmentation failed indeed, and I can choose to discard it from the analysis. So here you see how such a particular table for QC could help you pick up failures and create a curated list of cases for your analysis. And now, of course, I'm going to tell a bit more about those checks and what they actually test for. As more data came on the platform, we needed a way to ensure that the systematically met with some predefined specifications. And for this, we implemented what we called validators, which are like sets of checkpoints. Each is targeted at a very specific aspect of the data and returns either pass or fail. And then every new image is taken through some of these checkpoints according to the type of data, so that in the end, each new resource gets a checklist, like when you take your car to the mechanic. The results can be used for visual control, as they are stored in human-readable PDF, like this one, and also in JSON records for programmatic use. Now, to be honest, few people open these reports manually. We rather rely on the JSON files, for instance, to analyze quality over big samples or select cases programmatically, etc. Here, I want to stress on the standardization of the framework. All tests share the same template, which not only improves readability, but also, and most importantly, makes it easy to add new tests, no matter if it is structural, diffusion, pet data, functional, ASL, you name it. And in practice, validators are run automatically after each new import or each new processing job, just like any other XNAT pipeline. But you can choose to run a validator manually and locally on any given image just by running a simple Python command. Here I show one example of a validation report with a summary of the tests, see how they share all the same template. If you want to add your own, you just need to create a class that derives from tests with two functions, run and report, and you're good to go. Then in each test, you are virtually free to call any additional tool or library, NumPy, SciPy, or MRQC, that's your business. So in this case, that's for SPM12 multi-channel segmentation. We check that all the right expected outputs are there, that MATLAB version, SPM version is correct, that global volumes of gray white matter CSF are normal, whether execution time is normal, and there's also a snapshot of the result. We'll get back to this. The key message here is that all of this is executed automatically without anybody looking at it yet. Remember, this is how you can then collect this information in a big Excel table and filter out all potential failures. This is now for each pet session, some sanity check on identifiers. Basically, each test often derives from a real case scenario that we observed at some point and that we want to start controlling for. So scanner version, quite useful with scanner updates. Tracer name, dosage, subject weight, sequences, nifty conversions. This is for diffusion weighted imaging, DWI data processing. Here we use MRTrix for denoising. Hence, we use some of MRTrix's QC metrics in some tests to check for SNR, CNR, if they are higher than a certain threshold, outlier percentage, etc. That is for white matter lesion segmentation. You can find there a couple of snapshots. And so over the past few slides, you've seen two main types of tests, basically. Some tests that look for some parameter and check that it matches some target value. That's one type. And snapshots, typically, but not only for segmentation jobs. And that's another. And while validators can be handy for automatic controls, such as with the first type, with clear target values that can be dealt with automatically. With the other type, like when dealing with segmentation results, you will still need to go through some visual inspection, and that's why snapshots are needed. There's a variety of existing tools out there for brain data visualization to pick up from. However, here we needed a tool that would allow us not only to control the slices to include, but also the layout, the color map, label selection, especially with raw volumes, using contours or colored areas, static or animated renderings to see the raw intensities behind. That seemed to us like a well-defined problem that a specific module could be targeting at. And that's how nisnap was released. So that makes another reusable component, nisnap, useful with segmentations, whenever you have labels. And so in each validator checking for segmentations, there is usually a test that calls nisnap to generate one of these snapshots. So that's great. You have snapshots in the PDF reports, but still, that will require someone to look at them, and that's another story. Luckily, as I said, we have a special command with BX to collect all snapshots of one type over a large sample in one folder. What is harder now is to get people of your team to review those snapshots and to collect their review. And that makes my transition to the next part. But before that, time for our third example. Again, it's good to use your previous notebook. You'll have to pip install nisnap, and then you can try this example to get a snapshot, in that case, of some hippocampal subfields. So to facilitate the inspection of large collection of snapshots, we developed another very light independent module in JavaScript/Python called snaprate to allow multiple users to navigate and assign each snapshot with a score and some review. There's a demo online, so you can check for yourself. So sure, it needs the snapshots to be generated earlier, and you cannot inspect the data as you would do using a real nifty viewer, but we wanted a tool to be aimed at some degree of efficiency. In different terms, we believed that using snapshots that we can fine-tune to provide summarized representations of complex results may be a good way to make QC maybe easier, maybe faster, and more reproducible. In addition to this, you can also provide your reviewers with results from prior automatic tests to help with the review. That's those green and red buttons seen there. And it's also easy to link and switch between snapshots of different types or modalities from the same subject. All reviews are stored server-side in a single Excel spreadsheet, so that's very easy to collect. The admin can follow the general progress of the task, and again, it works independently, so with any JPEG files rendered using nisnap, matplotlib, or it can be your mobile phone pictures from your last pre-pandemic trip, so whatever. And in the end, that's a way to turn this tedious but still critical task to a collaborative exercise. You can control the distribution then, you get PIs, PhD students on board for training. That's quite open. This figure represents the components from the system and their integration with validators, BX, snaprate, nisnap, pyxnat. This is to illustrate the modularity of the whole thing, instead of being a monolithic system. Here we kept XNAT unchanged, as it was easier and more efficient to invest in tailored developments around it, each with its own mission. We actually have more types of integration, such as using instant messaging or dashboards to visually monitor the data, but I have to skip this for now for the sake of time. In the end, these are just additional efforts to bring users to the same data using different roadways, creating multiple interaction channels. And that brings us to the conclusion slide. Please allow me to stress one last time on some important points. Through this model, we advocate for giving multiple ways to access the same data, as data is there to be used. People in a group do not necessarily have the same skills or preferences, so the system should be flexible in that regard. Then QC is hard. Nobody wants to do it. It is very poorly standardized, yet it is necessary. So on one hand, let's try to automate the biggest part with clear target values whenever possible. And for the rest, well, let's get as many friends on board as possible and let's make their task easier, for instance, by creating some nice snapshots. And finally, again, we kept XNAT unchanged and came up with satellite components, resulting in a modular system that can be reused or adjusted based on the needs of a specific center. And with this, I would like to thank my fantastic colleagues from the Barcelona Beta Brain Research Center, with a special mention to Jordi Huguet and Marina García-Prat, who have been long-term key contributors to this whole work. Please feel free to contact me through Twitter, GitHub, or email if you have any questions or just to say hello. Thank you.